This video is about understanding and using coding. We need to be able to calculate the mean and standard deviation of the original data using the mean and standard deviation of the coded data and vice versa. So the general rule is the mean is affected by all four operations. So it's affected by adding, subtracting, multiplying, and dividing. A standard deviation, however, is only affected by multiplying and dividing. Okay, so all four operations affect the mean, but a standard deviation is only affected by multiplying and dividing only. Okay, the reason why it's not affecting by adding and subtracting is because the whole data moves. Obviously, if you add and subtract a certain value from all the data points, which means the x bar will also move. So the distances between the deviations from the mean of the data to each data point does not really change. Therefore, if x is equal to, if the formula y is equal to x minus a over b is used for coding the original data x into coded data y, then first of all y bar will be equal to the original mean, because it's the mean is affected by subtracting and dividing, so it's going to be x bar minus a over b. Also, the standard deviation of y will be equal to the standard deviation of x. Subtracting does not affect the standard deviation, but dividing by b does, so it will be divided by b. That's it. And also, if I wanted to do the variance, which is sigma of y squared, then it was the same thing as sigma of x squared. Now, because the variance is the square of the standard deviation, it'll be over b squared. Okay, so a thing to keep in mind, that variance changes by dividing by b squared. Okay, let's look at some examples now. Scientist measures the temperature x degrees in degrees Celsius at 5 different points in a nuclear reactor. Her results are given below. A. Using coding y is equal to x minus 300 over 10 to code this data. So the first value will be 332 minus 300, which is 32, divided by 10, which is 3.2. 355 divided by 300, take away 300 is 55, divided by 10 is 5.5. 306 take away 300 is 6, 6 divided by 10 is 0.6. 317 take away 300 is 17, 17 divided by 10 is 1.7. And 340 take away 300 is 40, divided by 10 is 4, so 4.0. B. Calculate the mean and standard deviation of the coded data. So y bar is the coded data, which is sum of y over n, which is 3.2 plus 5.5 plus 0.6 plus 1.7 plus 4.0 divided by 5, which works out to be 3. Okay, and then now I need to work out the standard deviation of the coded data, which is sigma y, which is sum of y squared over n minus y bar squared, which is equal to square root of 3.2 squared plus 5.5 squared plus 0.6 squared plus 1.7 squared plus 4.0 squared, all over 5 minus 3 squared. And I end up getting 1.716974, blah, 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 which is equal to 1.72 to 3 significant figures. So you use your answer to part B to calculate the mean and the standard deviation of the original data. So C, so y bar will be equal to x bar minus 300 over 10, because the mean is affected by subtracting and dividing, which implies if I rearrange it, I get x bar is equal to 10 times y bar plus 300, which means it's going to be x bar will be equal to 10 times 3 plus 300, which is equal to 330. Okay, again, sigma of y, so the standard deviation of y is equal to, because it's only affecting by dividing, it will be the standard deviation of x divided by 10, which means that the standard deviation of the original data, which is x, will be equal to 10 times the standard deviation of the quoted data, which is 10 times sigma y, which implies you get sigma x is equal to 10 times 1.716974. So I'm using the non-rounded version, which is equal to 1. Times by 10, which is equal to 17.16974, blah, 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 which is equal to 17.17. Okay, so you use your answer to part B to calculate the variance of the standard deviation. So it's variance of the original data, sorry. So D will be equal to answer to part B. So the standard deviation of the coded data. So the coded data, so sigma of y is equal to 1.716974. So the variance of y will be 1.716974 blah 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 squared, which is equal to 2.948, so on. So now if I know the variance of y, which is the coded data, it will be equal to the variance of the original data divided by 10 squared, which is 100. So which means if I rearrange to make the variance of the original data, which is sigma squared x, it will be 10 squared, which is 100, times sigma squared of the coded data. So variance of the coded data, which is 100 times 2.948, blah, 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 which is equal to, it's not, actually it's 2.948 exactly. So 100, which gives me 294.8. So that would be my answer. From the large data set, the maximum gust G in knots is recorded in Luches during May and June 2015. The data was coded using H is equal to G minus 5/10, and the following statistics found. So the S of HH is equal to 43.58, H bar is 2, and N is equal to 6 to 1. Calculate the mean and the standard deviation of the maximum gust in knots. Okay, so we have H bar is equal to G bar minus 5/10. So we want to find G bar, so I need to rearrange to make G bar the subject of the formula. So I get 10 times H bar plus 5, which implies G bar is equal to 10 times H bar is 2 plus 5, which is 25. The standard deviation is, so sigma of H, which is the coded data, is equal to sigma of G, and because it's a standard deviation is only affecting by dividing, divide by 10, which implies sigma of G is equal to 10 times sigma of H, which is the coded data. So the first thing I need to do is work out sigma of H. And if I do it here, with the standard deviation of the coded data is equal to square root of S of HH over N, which is equal to square root of 43.58 over 61. So remember this version of this standard deviation formula is in the formula booklet, which is 0.845233 in your calculators, which rounds to 0.85. But we're not going to use, we're going to use a non-rounded answer, so let's just leave it as that. Let's not round the answer. So that means if I go back here, sigma of G will be 10 times sigma of G, which is the original data, is 0.845233 times 10, which I've already written down, which is 8.4525 2, 3, 7. Okay, that was a 7 there. And that was a 7 here, which is 8.45 when rounded. Okay, calculate the variance now. So this variance is going to be, first of all, is sigma of h squared is equal to sigma of g squared, which is variance over 10 squared, which is 100, which implies the variance of the original data is equal to 100 times sigma of h squared. Now sigma of h, if I go back here, which is the variance of h, is equal to just SHH over n, which is 43.58 over 61, which is equal to 0.714426. So all I need to do is 100 times 0.714426, which is equal to 71.4426, blah, 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 which is 71.44. That's it. Question 4, the next question. The coding y is equal to x minus 40 gives a standard deviation for y of 2.34. Write down the standard deviation of x. So sigma of y, so standard deviation of y is equal to 2.34. Now using the coding data, sigma of y is not affected by subtracting 40, so it's just going to be the standard deviation of the original data, which means sigma of x is equal to 2.34, as standard deviation is not affected by subtracting. Okay, next question. The weekly income I of 100 women workers were recorded. The data was coded using y is equal to I bar I minus 90 over 100, and the following summations were obtained. Sum of y is equal to 131. Sum of y squared is equal to 176.84. Estimate the standard deviation of the actual women workers' weekly income. So if I were to work out this standard deviation of the coded data, which is sigma of y, it will be square root of sum of y squared over n minus sum of y over n squared, which is just mean, which is equal to sum of y squared is 176.84 over 131 minus, not 131, sorry, it's 100. 131 is sum of y. So n is 100. Do you think there? So it's going to be minus 131 over 100 squared. If I put that into my calculator, I end up getting 0.22869193, blah, 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 which is equal to 0.23 when rounded. But maybe we don't need to round it because we're going to use this answer, so let's not round it. So that is sigma of y, which is the standard deviation of the coded data. So if I want to work out, find the formula, then they're related by, obviously, the standard deviation of the coded data, because standard deviation is only affected by dividing, same thing as sigma of yi over 100, so just dividing by 100, which implies the sigma of I is equal to 100 times sigma of y, which is 100 times 22 point, oops, I'm already dividing there, 100 times, sorry, timesing, 100 times 0.22869193, blah, 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 which is equal to 22.869193. When rounded, that becomes 22.87. The next question, a meteorologist collected data on the annual rainfall in millimeters at 6 randomly selected places, so n is equal to 6. The data was coded using s is equal to 0.01x minus 10, and the following summations were obtained. Sum of s equals 16.1, sum of s squared is 147.03. Work out the estimate for the standard deviation of the actual annual rainfall. So first thing we need to do is work out the standard deviation of the coded data, which is equal to sum of s squared over n minus sum of s over n all squared, which is equal to 147.03 over 6 minus 16.1 over 6 all squared, and we end up getting 4.159894497. Now if we look at it, sigma of s, so remember standard deviation is only affected by multiplying and dividing, so it's just going to be 0.01 times sigma of x, which implies sigma of x, which is original data. Standard deviation of the original data is equal to the standard deviation of the coded data divided by 0.01, which means that we get 4.159894497 divided by 0.01, which actually makes it 100 times bigger, which means we get 415.98944497, which is, when rounded, 415.99. A teacher standardizes the test marks of his class by adding 12 to each one and then reducing the mark by 20%. If the standardized marks are represented by T and the original marks by M, A, write down a formula for the coding the teacher has used. So that means if the standardized is T, that's what we're obtaining after we've done a calculation, then we take the original mark, which is M, I add 12, and then I times by 0.8. So it's the same thing as 0.8 times M plus 12, which when we expand it, we end up getting 0.8M plus 12 times 0.8, which is 9.6. So I prefer it in this way without brackets, because we're used to seeing coding like that. So that implies T is equal to 0.8M plus 9.6. Okay, the following summary statistics are calculated for the standardized mark. So you've got N, you've got T bar and S of TT. Calculate the standard deviation of the original marks gained. Okay, first we need to work out the T bar and sigma T. So T bar, we know what T bar is already, so T bar would be equal to, because the mean is affected by both multiplying and adding, it will be 0.8 times M bar plus 9.6. Now we're trying to find an M bar, so we need to rearrange to make M bar the subject of the formula. So it's the same thing as T bar minus 9.6 divided by 0.8. So it's the same thing as 52.8 take away 9.6 divided by 0.8, which gives us a value of 54. So T bar, therefore, T bar is equal to 54. Okay, so next thing we need to do is first we need to work out the standard deviation of T, because we don't know the standard deviation of T. Which is, so the sigma of T is equal to square root of S of TT over N, which is equal to square root of 7.3 over 28, which is equal to 0.510618, blah, blah, blah. And because we're going to use that to find the standard deviation of the original mark, let's just leave it non-rounded. Now, because standard deviation is only affected by multiplying and dividing, sigma of T is equal to 0.8 times sigma of M, which means if I rearrange it, I get sigma of M is equal to sigma of T over 0.8. Oops. Which means we get 0.510618 divided by 0.8, which is equal to 0.638252, which means sigma of M is equal to 0.64 when rounded to 2 decimal places. Just realize I labeled this wrong. This is not T bar, this is M bar, which is the original mark. A biologist recorded the height x centimeters of 20 plant seedlings. She calculated the mean and standard deviation of her results. X bar is equal to 3.1 and sigma is equal to 1.4. The biologist subsequently discovered she had written down one value incorrectly. She replaces a value of 2.3 with a value of 3.2. Calculate the new mean and the standard deviation of her data. So before we can do anything, we need to work out the new sum of x and the new sum of x squared. So x bar is equal to sum of x over n, which implies 3.1 is equal to sum of x over 20. Which means before, sum of x will be equal to 3.1 times 20, which is equal to 62. So the original sum of x is 62. But obviously, the biologist did a mistake. So 62, because she's replaced a value of 2.3 with 3.2, you should take away 2.3 plus 3.2, which is equal to 62.9. Now this is equal to the new sum of x. Okay, that means the new x bar will be equal to the new sum of x over n, which is 62.9 over 20, which gives a value of 3.145. So that's the new x bar. Now sigma is equal to square root of sum of x squared over n minus x bar squared. Which implies if I want to make sum of x squared the subject of the formula, sum of x squared will be equal to sigma squared plus x bar squared times by n. Which means sum of x squared will be equal to sigma squared, which is 1.4 squared, plus the original x bar, which is 3.1 squared, times by n, which is 20. Okay, now when we put this into our calculator, we get 231.4. So that's the original sum of x squared. But we need the new sum of x squared. So the new sum of x squared will be equal to 231.4, take away 2.3 squared. Just realized I didn't add there. Add 3.2 squared, which gives us a value of 236.35. So the new sigma will be equal to square root of new sum of x squared over n minus new x bar all squared, which is equal to square root of 236.35 over n, which is 20, minus 3.145 all squared, because that's the new mean squared, which gives us a value as 1.387975, which is equal to 1.39.